theorem says that the total work applied on an object equals the change in that object's kinetic energy, where the kinetic energy of the object is the object's energy stored in its what? Kinetic energy is energy stored in what?
Mass.
Not in mass. In what aspect of the object's motion? No, sliding has to do with kinetic friction. What aspect of the object's motion does kinetic energy depend upon? It does depend upon mass, but we wouldn't say that kinetic energy is the energy stored in mass. It's the energy stored in the object's speed. It's the energy stored in the object's movement. Okay? So we would say that kinetic energy is the speed, is the energy stored in an object's speed, and it's just 1/2 mv squared. Okay? It does depend upon mass, but we refer to kinetic energy as the energy stored in an object's speed. Okay? The energy stored in an object's mass is a different equation. It's Einstein's famous equation, E equals mc squared. That's something we won't cover in this class. That's something that you guys might see at the end of physics 2. Okay? Really quickly, you guys should just know this as a rule of thumb for deltas. First of all, delta is always the change in. So delta K is the change in K, and it's always final minus initial. So if the final is greater than the initial, you have a positive delta. If the initial is greater than the final, you have a negative delta. And if the final equals the initial, your delta is what?
0.
0. Okay? So if your delta is positive, this means that you have an increase in your value, because the final is larger than the initial. The object ends with more than it started with. So its value increased. If delta is negative, then the value decreased, because its initial is greater than its final. It started with more than it ended with, so its value decreased during the motion. And if delta is 0, then there is no change in the quantity, because the final equals the initial. Okay? This is important because the work energy theorem relates the total work to the delta of kinetic energy. Not to kinetic energy itself, but to the delta of kinetic energy. So if the total work is positive, what does that mean about kinetic energy?
Increasing.
It what?
It's increasing.
It increased, right? If the total work is positive, that means that delta K is positive, and a positive delta means that K increased. Then K increased. What does that mean about the speed of the object? Its speed what? Increased. If its kinetic energy increases, its speed increases. And its speed increased. Okay? If W total is negative, then what happened to kinetic energy? Right? It decreased. Anytime you have a delta that is negative, you have a decrease in the quantity. And so what happens to the speed? The speed decreased as well. What about if the total work is 0? What happens to the kinetic energy?
There's no change.
It's not stationary. There is no change in the kinetic energy. So this is an important point to make, so I'm glad that you said that. If the total work is 0, it does not mean that the kinetic energy is 0. It means that the delta of the kinetic energy is 0. It means that the change in the kinetic energy is 0. Okay? So if the kinetic energy is 10 joules when the object starts moving, if the total work is 0, the kinetic energy would be 10 joules at the end of the motion. Okay? It doesn't mean that the kinetic energy is 0. It simply means that it's not changing.
Can you give three quick scenarios for all the three?
I'm going to color some, okay? All right. If the total work is 0, then kinetic energy doesn't change or didn't change. And what happened to the speed? Right, the speed remained the same. All right. We are going to use the work energy theorem as a guide to make sure that when we calculate the work due to individual forces, that we get the sign correct for those forces. All right? Let's imagine the scenario of me throwing an object upward. Okay? So an object is thrown upward. This object has a mass of 3 kilograms, let's say. And I want to know how much work gravity does as this object moves up an amount 4 meters. Okay? I want to know what is the work done by gravity as the object moves up 4 meters. Okay? I gave you guys a formula last class to calculate the individual work done by any force. That formula is that the work is the dot product between the force and the displacement the object undergoes. Okay? In this scenario, like in most scenarios, we will know the 2 vectors, the force and the displacement. We will know them in magnitude and direction form. So I will use the magnitude and direction form of the dot product. Okay? If you know that some vector A has a magnitude of A, and some vector B has a magnitude of B, and they're separated by some angle theta, then the dot product, A dot B, is the magnitude of A times the magnitude of B times the cosine of the angle between the 2 vectors. Okay? It's really important to understand that this angle is the angle between the 2 vectors. It's not the direction of either vector A or vector B by itself. Okay, but it's the angle between the 2 vectors. For this problem, we would then say that the work done by gravity is going to be the force of gravity, which I'll just call Fg. I'm not going to use W because I don't want to confuse it with work. Okay? But the force of gravity is just the weight. okay, dot the displacement. Using this formula, I can say that the dot product is equal to the magnitude of the force of gravity times the magnitude of the displacement times cosine of the angle between the force of gravity and the displacement. Okay? Where does the displacement point if the object is moving upwards? The displacement does not point downward. Where does the displacement point if the object is moving upward?
Up.
It points upward. It points in the direction that it moves. If it starts here and it ends here, then the displacement points upward. Where does the force of gravity point? Downward, right? Gravity always points downward. So the force of gravity is downward. So if the displacement is upward and the force of gravity is downward, what is the angle theta between the two? 180 degrees. So in this problem, theta is 180 degrees. Okay? So we know what theta is. What's delta x, the displacement? 4 meters, right? It travels upward 4 meters. What is Fg, the magnitude of the gravitational force?
30.
It's going to be 30 in this case. How'd you get 30?
3 times 10.
Yep. So if the mass is 3 kilograms, then the force of gravity is mass times gravity. This is just the weight. But once again, I'm not using the letter W because the letter W is used for work in this chapter and the next one. So to avoid confusion, I'm just calling it the force of gravity. So it's M times G. M is 3 kilograms, G is 10. So this is 30 newtons. So if we plug in these numbers, the force of gravity is 30, the displacement is 4, cosine of 180. Does anyone know what cosine of 180 is? You also have a calculator, just so you
One.
negative 1. Cosine of 0 is positive 1, okay?
180 is probably.
So we get negative 120, right? And the units are joules. Okay? I want to understand why the work due to gravity is negative. And the way to understand why the work due to gravity is negative is by understanding this right here. These points that I made right here. Okay? As my object goes upward, what is gravity doing to the speed of the object? It's slowing it down. As my object travels upward, gravity is acting to decrease the speed of the object. Okay? Any force that acts to decrease the speed of the object will also act to decrease the kinetic energy, and therefore it should produce a work with what sign? Negative. Okay? The work is negative because gravity acts to decrease the object's speed. Okay? You can always ask yourself, in this situation, is the force acting to speed the object up, or is the force acting to slow the object down? Or, in some cases, is the force not having any effect on the speed at all? Okay? Based on that, you can deduce what the sign of the work should be. Yeah.
Maybe a miss, but so the negative basically means that work is being done.
No, the fact that the number is not 0 means that work is being done.
Okay. So what difference does negative or a positive joule make?
So the negative sign tells us that gravity is acting to slow the object down,
Okay.
which is true because the object is going up.
Mhm.
If the sign was positive, it would mean that the force was acting to speed the object up, which
Okay.
isn't true in this case.
So basically, you say the force of gravity is greater than.
No, not greater than anything.
Okay.
I'm not saying that the force of gravity's magnitude is greater than anything. All that I'm saying right here is that this negative sign of the work tells us that gravity is acting to slow the object down.
Okay.
As I throw the object up into the air, as it travels upward, what effect does gravity have? That pull downward towards the surface of the earth, towards the center of the earth.
Mhm.
What effect does that pull downward have on the speed of my marker when I throw it up?
Speed decreases.
The speed decreases. Any force that acts to slow an object down produces a negative work.
Okay.
Does that mean that the work due to gravity will always be negative?
No.
No, because there are situations where gravity can act to speed an object up. What if
So this is basically the gravity is
I were standing on a building
gravity is working, so that's
and I dropped an object off of the edge of the building? This object has, let's say, a mass of 7 kilograms, and the building has a height of 20 meters. Okay? What I want to know is how much work, A, how much work does gravity do as the object falls to the ground? Okay, so I'm saying that the object starts on the edge of the building and falls to the ground. So that defines the displacement of the object. What's the magnitude of the object's displacement? 20 meters. Right? Because I said that it falls to the ground. What if I said, how much work does gravity do as the object falls to the midway points of the building? Then it would be 10, right? Okay? What direction is the displacement going to be? Down, because the object is moving downward. It starts up here and it ends down here. So the displacement is pointing down. Okay? The work due to gravity is going to be the force of gravity dotted with the displacement, which is going to be the magnitude of the force of gravity times the magnitude of the displacement times cosine of the angle between the two forces. Where does the force of gravity point? Down. So what is theta, the angle between the force of gravity and the displacement? It's 0 for this problem. If they're both pointing down, then the angle between these two vectors is 0 degrees. Okay? We already said that the magnitude of the displacement was 20. What's the magnitude of gravity? We can find it by m times g. 7 times 10, which is 70 newtons. So the work is 70 newtons times 20 meters times cosine of 0. Cosine 0 is positive 1. So 70 times 20 is 1,400 joules. And it's positive 1,400 joules. Why is the work due to gravity positive in this case?
Because the speed is increasing.
because gravity is acting to speed the object up. Okay, when you hold the object at rest and you let it go, gravity pulls that object down, and gravity is acting on that object to speed it up. If a force acts to increase an object's speed, then it acts to increase the object's kinetic energy, and if delta K is positive, then that work should be positive. Okay?
Oh, so basically this is the proof why this is the case, why we just wrote everything down.
No, I didn't prove why this formula is true.
Okay.
I'm just using the concept of this formula to show why these signs are correct. Okay, so any questions with part A for this problem? Okay, now part B for this problem is going to be if the object is dropped from rest, what speed does it hit the ground with? We can answer this question using the work energy theorem. As the object is falling, what forces are acting on the object? Gravity is acting on the object. What else?
Normal force.
What's required for there to be a normal force? A surface. As it's falling, is there a surface? No. What other forces can you guys think of? What about friction? No. What's required for friction? A surface. Okay, what other forces? Tension?
No.
No. Why not? No rope. What about a spring force? No, right? Because you need a spring. Okay, so what forces are acting on that object as that object falls? Only gravity. Okay? So we can use the work energy theorem because we know every force acting on the object, so we can calculate the total work done. The total work is just the sum of the work done by every force on an object. Okay, that's all the total work is. The total work is the sum of the work done by each force on an object. Okay? That's all the total work is. In this problem, we know that there's only one force acting on the object, so there's only one work to consider, which is the work due to gravity. So in this problem, the total work done is just the work done by gravity, which we calculated was 1,400 joules. What does the work energy theorem tell us the total work equals? The change in the object's kinetic energy. Okay, this just says W.E.THRM, so work energy theorem. I just put theorem with no vowels. Okay, that way I don't have to write out work energy theorem. Okay? Delta K, remember, is the final minus the initial. So this is going to equal K final minus K initial. If the object is dropped from rest, what's its initial kinetic energy? 0, right? Kinetic energy right here depends upon speed. If the speed is 0, what's the kinetic energy? If the speed of an object is 0, if V is 0, what's the kinetic energy?
Man.
0. What? No, what'd you say? Okay. So if V is 0, then K is 0. Okay? So the initial kinetic energy is 0, meaning that this total work, these 1400 joules, are equal only to the final kinetic energy. Okay, that's what the work energy theorem tells us. The work energy theorem tells us that the final kinetic energy is 1400 joules. Okay? The final kinetic energy is just equal to 1/2 times the mass times the final speed squared. So this is equal to 1/2 times the mass times the final speed squared. Okay? If you solve this formula, you multiply the 2 up, divide by the m, that gives you v squared, and so you take the square root. So v final is the square root of 2 times 1400 divided by the mass, which is the square root of 2 times 1400 divided by, so the mass was 7. So it's 400, square root of 400 is 20. So it's 20 meters per second. That's the speed that it hits the ground with.
That says half and the final squared.
Yeah. It's just the kinetic energy final. Okay? Really quickly, for those of you guys who can't see it, what I wrote in that corner down there is K final equals 1400 joules. So 1/2 m V final squared is 1400. And so V final is the square root of 2 times 1400 divided by m. M is 7. So 2 times 1400 divided by 7 gives us 20 meters per second. So the speed that the mass has right before it hits the ground is 20 meters per second. Okay? Any questions? By the way, we can double check this answer and we can make sure that this answer is correct. Could we use kinematics to solve part B for this problem?
Yes.
What's the requirement to use kinematics? What must be true?
Acceleration will be constant.
Acceleration must be constant. What is the acceleration of the object as it falls?
10.
Right, just gravity, 9.81 or 10. Okay, but the point is that it's just the gravitational acceleration. Is that constant near the surface of the Earth?
Yeah.
Yes. So could we use kinematics to find the final speed of the object right before it hits the ground?
Yeah.
Absolutely. So let's double check our answer and confirm that it's correct by using kinematics, which we're more familiar with. We can use the formula v squared equals v naught squared plus 2a delta x. What's the initial speed here when it's released?
0.
0. So the final speed is the square root of 2 times a times delta x. 2 times, the acceleration is gravity, so it's 10. Delta x is 20. 2 times 10 is 20 times 20. What's the square root of 20 times 20? 20. So you see, kinematics tells us that we got the right answer. Okay, physics works regardless of what approach you use, as long as you obey the rules. Okay? Any questions about that problem? All right. Let's let's imagine an object that is pulled along the floor. Okay, so this object has a mass of, let's say, 10 kilograms. Okay, and it's pulled along the floor by a force Fp equals, so hold on 1 second. So let's say by a force of 40 newtons, that makes an angle of 30 degrees with the horizontal. Okay? In between the box and the ground, there's a coefficient of kinetic friction of 0.3 newtons. I need to actually make this 40 newtons a little bit bigger. Yeah. Let me make this, let me make this 60 newtons. Okay. I just want the answer to make sense. Okay? So an object is being pulled along the ground by a force of 60 newtons that's angled up by 30 degrees. Did I see? I thought I saw someone raise their hand. Yeah. 0.3, that's the coefficient of kinetic friction between the box and the ground. Okay? Any other questions? All right, so part A, what is the work done by each force on the box if it moves 5 meters to the right? Okay? B, what is the total work done on the box if it moves 5 meters to the right? Okay? And C, if the box is initially moving at 5 meters per second to the right, how fast will it be moving after, or I'll say, what will its speed be? I want as little confusion as possible. What will its speed be after moving 5 meters to the right? Okay. So this question is basically identical to this question, it just involves more forces. So it's a more complex form of the same question. Okay, let's start with question A. What is the work done by each force on the box? Before we can answer part A, we first have to identify what forces are acting on the box. Okay? So let's draw a free body diagram of these forces.
Friction.
Okay, what forces are acting on the box?
Friction.
Friction, what kind of friction?
Kinetic.
Kinetic. Why kinetic?
Because it's
Sliding, right? What direction does kinetic friction point?
to the left.
To the left. Why?
Because it opposes the sliding
Right.
of the object.
And it's sliding to the right. This object has a velocity to the right. Okay? So there is a kinetic friction to the left. I heard a normal force. Where's the normal force point?
Down.
Not down.
Upward,
Up.
perpendicular to the surface.
Also.
Perpendicular to the surface.
The normal force points up because it
Oh,
has to
yeah,
support the object upward to prevent it from dropping downward.
Yeah.
Okay? What other forces?
Gravity.
Gravity, which points where?
Down.
Down. And remember, I'm calling it the force of gravity here. I'm not calling it W, the weight, because we're dealing with works here, and I want to avoid that confusion. Okay?
And there's the pulling force.
And then there's that pulling force, which acts at a 30-degree angle above the horizontal. Okay? Any other forces? The one pointing to the left is kinetic friction. Okay? Any other forces? What about tension?
No.
Spring force? No. Okay? What about static friction?
No.
No, right? Friction's either kinetic or static, and it's kinetic in this case. All right, so part A, what is the work done by each force on the box? So we need to calculate this formula for each force individually. Okay? What direction is the displacement for this box?
To the right.
To the right. This box is displacing to the right. What's the magnitude of the displacement? Five meters. Okay, the displacement is to the right. Okay, so we have four forces. We have to calculate the work done by each of those four forces. So part A, the work done by gravity is going to be the force of gravity, the magnitude, times the magnitude of the displacement, times cosine of the angle between the force of gravity and the displacement. What's the angle between the force of gravity and the displacement in this problem? No.
Oh,
The displacement points to the right. Where does gravity point?
down.
Down. What's the angle between the right and down? 90 degrees.
So just
Oh, sorry, I heard 30.
no.
Sorry. Okay, the displacement, delta x, is to the right. The force of gravity is down, and that's a 90-degree angle. What's cosine of 90? 0. So the work done by gravity is 0. Okay? Any questions? Gravity should produce no work in this problem because it acts perpendicular to the velocity. Okay? It's really important to remember the rules of acceleration and speed that I had shown you guys before. There are 3 situations involving acceleration and speed, okay? You have the situation where the velocity and the acceleration point together, in which case the speed does what? It increases. There's the case where the acceleration and the velocity point in opposite directions, in which case the speed does what? It decreases. And then lastly, there's the case exactly halfway in between these two, where this acceleration and the velocity are perpendicular to one another. And what happens to the speed? Stays the same. No change. in speed. Okay? Since the force of gravity is perpendicular to the velocity, which is to the right, the acceleration that would be produced by gravity would fall under this situation and therefore would produce no change in speed. No change in speed means no change in kinetic energy. No change in kinetic energy means no work. Okay, so the force of gravity should produce a work of 0. Okay, what about the work due to the normal force? It's going to be the magnitude of the normal force times the displacement times the cosine of the angle between the normal force and the displacement. What's the angle between the normal force and the displacement? 90, right? The displacement is to the right, and the normal force is up. That produces a 90-degree angle, so how much work does the normal force produce? 0. Is this what you guys should expect?
Yeah.
Yes, because once again, the normal force should fall into this situation. Okay? Now, what about the work due to friction? This is the magnitude of kinetic friction times the magnitude of the displacement times cosine of the angle between them. What's the angle between the kinetic friction and the displacement? 180. The displacement is to the right and friction is to the left. The displacement, delta x, is to the right and kinetic friction is to the left, so the angle between them is 180 degrees. Okay? Before we can calculate this though, we need to first determine what the kinetic friction is. Okay? Is the kinetic friction an adaptive or a non-adaptive force? It's non-adaptive. That's critical to know, because since it's non-adaptive, you could on an exam flip to the formula sheet and find yourself a simple formula to calculate the kinetic friction. Is there going to be a simple formula to calculate the magnitude of an adaptive force? No, right? How do you find adaptive forces?
We don't know the formula.
There is no formula. What do you have to do? Newton's second law, okay? So it's important to know that kinetic friction is non-adaptive, meaning that it has a formula, okay? The formula for kinetic friction is the coefficient times the normal force. Now, we don't know the normal force either. Is the normal force adaptive or non-adaptive?
Adaptive.
That's adaptive. How do we solve for adaptive forces? Newton's second law, okay? Newton's second law tells us that the forces along the vertical direction should be what? Balanced or unbalanced? Balanced. Because this box has no vertical acceleration. This box's motion is purely horizontal, so it has no vertical motion, meaning that the forces along the vertical axis should be balanced. Okay? Before we can balance them, though, we have to break up the pulling force into its components. Okay, did you have a question?
No.
I thought I saw a hand up. Okay. It's going to have an X component, and it's going to have a Y component. Which one is the cosine, the X or the Y? The X component, right? Because that's the axis that touches the angle. Okay? So, the pulling force in the X direction is the pulling force times cosine of 30 degrees, which is 60 newtons, times cosine of 30 degrees, which is 52 newtons. Okay? The pulling force in the y direction is the pulling force times sine of 30. Sine of 30 is 1/2, so 60 sine of 30 is just 30 newtons. Okay? To balance the y-axis, we say that the sum of all forces up equals the sum of all forces down. Okay? Y-axis is balanced. So, the sum of all forces up is the normal force plus the pulling force in the y direction. And that equals the sum of all forces down, which is just the force of gravity. Okay? So the normal force is going to be the force of gravity minus the y component of the pulling force. Last thing, we have to calculate the force of gravity really quickly. That's just mg. M I said was 10. G is 10. So the force of gravity is 100 newtons. Okay? So the normal force is 100 newtons minus the y component, which is 30. So the normal force is 70 newtons. Okay? We did a bunch of problems before about how to calculate the normal force. You always calculate it by solving Newton's second law because it's an adaptive force. Now that we know the normal force, we can find friction. Why do we need to find friction again? What are we trying to do in this problem? Find the total work done. The work done by friction, okay? So there are a lot of steps in this problem, and you don't want to get lost in the steps. Okay, we want to keep sight of the goal. The goal ultimately is to calculate the work done by friction, so we need to calculate the magnitude of kinetic friction. The coefficient of kinetic friction in this problem is 0.3. The magnitude of the normal force we said was 70 newtons, so that's like 21 newtons. 70 times 0.3 is 21. Okay? So, now we can plug in all of our numbers. The magnitude of friction is 21 newtons. The displacement, I said, was 5 meters. And the angle is 180 degrees. Cosine of 180 is -1. So 21 times 5 is 105, so the work done by friction is -105 joules. Okay. Any questions about the work done by friction? Once again, it's just an application of the same formula that we've used to calculate the work done by any other force. The reason why this calculation took so long was because of the calculation of the friction itself. Okay, but calculating the work done by friction is the same as calculating the work done by any other force. Okay? Any questions? All right, last force. How much work does the pulling force produce? So it's the force of the pull times the displacement times cosine of the angle. The displacement is to the right, and the pulling force is 30 degrees above the horizontal. So the angle between these two is 30 degrees. The magnitude of the pulling force, I said, was 60 newtons. What was the displacement again? What? 5 meters. And cosine of 30. That's negative 260, sorry, positive 260 joules. Okay. Really quickly, should the work due to friction be negative? Does it make sense that the work due to friction is negative? Why? Why does it make sense that the work due to friction is negative?
Because the kinetic friction is going that way, as opposed to the.
So that's a mathematical explanation, and that's correct. That the angle between them is 180, so the cosine of 180 is -1. But I want a conceptual explanation. Because friction acts to slow the object down. Okay? Friction acts to slow the object down. Any force that acts to slow an object down produces a work that is negative. Okay? That's an important conceptual thing to understand. Okay? Now, the pulling force. Why does it make sense that its work is positive?
It's going in the same direction as the other.
So what's it doing to the speed?
Increasing.
It's increasing the speed. The pulling force is acting to speed the object up. As we pull the object to the right, if it's already moving to the right, what's happening to the speed? It's increasing. If the acceleration and the velocity point in the same direction, the speed increases. So the pulling force is acting to speed the object up, so it should absolutely produce a positive work. Okay? Going into this problem, before you made a single calculation, you should have been able to predict what the sign of each work should have been. Just by looking at this free body diagram, you should have been able to say the pulling force will speed the object up, so its work should be positive. Friction will slow the object down, so its work will be negative. Gravity and the normal force act perpendicular to the velocity, so their works will be 0. Okay, before you do a single calculation, you should have been able to predict those characteristics of the works. Yeah. I gave it. It was given in this problem. I said just imagine that you're pulling this crate with a force of 60 newtons 30 degrees above the horizontal.
Why do you use it to find that next component?
Sorry. Oh yeah, you needed to find the components of it in the free body diagram. Okay? Any other questions? All right, so that's part A. All right? Part B is quick. The total work is just the sum of the individual works. Work is a scalar, not a vector. So to find the total work, you use simple scalar addition. You're just adding numbers together. It's not like vectors, because if you want to find the total force or the net force acting on an object, you have to break all the forces up into their x components and their y components. You add all the x components together to find the x component of the net force. You add all the y components together to find the y component of the net force. And then you know the components of your net force. You use the Pythagorean theorem to find the magnitude. Okay? The nice thing is that work and energy in general are scalars, so they obey the simple mathematics of scalars. So the total work is just the work due to gravity, plus the work due to the normal force, plus the work due to friction, plus the work due to the pull. The work due to gravity is 0, the work due to the normal force is 0, the work due to friction is negative 105. And the work due to the pull is positive 260. So it's 155, right? So positive 155 joules. Now, does it make sense that the total work should be positive?
Yes,
Why?
because it's moving.
No, not because it's moving.
Why?
This one's a little bit harder to explain than the individual works. In order to justify the total work being positive, you need to know whether this object in total is going to be speeding up or slowing down.
Because of that.
Because of what?
Like the explanation.
But you don't know what's the net force acting on this object. I never calculated the net force. We can say individually how each force acts. Clearly, kinetic friction acts to slow the object down. The pulling force clearly acts to speed the object up. But I'm asking about the cumulative effect of all forces. Is the cumulative effect of all forces going to result in the object speeding up or slowing down? That question is harder to answer. How do we know, by looking at these forces, that this object does indeed speed up as opposed to slowing down? The total work is positive, so that means what about the speed of the object? It's speeding up. No, it's not that it's moving, it's specifically that it's speeding up. If the total work is positive, it means that there is a positive change in the kinetic energy. So it's not enough to say that it's moving. We have to know that its speed is increasing. Okay? How do we know from this free body diagram that the speed of this box is increasing?
Oh, because it's greater than 60? Oh.
Nope. We have to look at the x direction, the direction of the motion. Okay? And we have to look at the two competing forces in the x direction.
Because the pull bigger than
Not the pull, but the x component of the pull. So close. But the x component of the pull is 52 newtons. And what's friction? 21 newtons. So if I draw the free body diagram, but I only focus on the x forces, the forces in the x direction, then what we have is we have the pulling force in the x direction, which is 52 newtons, and we have kinetic friction, which is 21 newtons. So what direction is the acceleration going to point? Or what direction is the net force going to point? To the right. The net force points to the right. So what direction does the acceleration point according to Newton's second law?
to the right.
It points to the right. If this object is already moving to the right, if it already has a velocity to the right, then what's happening to its speed?
Speeding up.
Its speed is increasing. Okay? So the final answer is harder to justify. Okay? These individual works are easy to justify. The final answer is harder to justify. Okay? But if I were to ask you in part B, what if I didn't ask what's the total work done, but I asked you the question, is this object speeding up or slowing down? That question would be easy to answer without having to deal with these forces. If you know the work done by each force individually, and the question is the object speeding up or slowing down, you can calculate the total work done, and if the total work is positive, then what's the object doing? The object is speeding up.
So you're saying you can't just look at it from the x-axis and just look at those two forces?
You can.
on it?
You can, but it's not the two forces, that's the thing. It's not comparing this force to this force. It's the x component of that force to this force. You can, I'm just saying that it's more complicated.
Okay, so whenever the x
So
component.
hold on one second. Yeah.
So the second law only works for like the y-axis, so then.
No, the second law works for both axes. Okay? When I applied the second law to the y-axis, the acceleration along the y-axis is 0. So I isolated that axis on its own. When I'm looking for the total acceleration of the object, when I'm looking for the net force, I look at the x-axis alone because the y-axis cancels. So the y-axis doesn't come into play when we're looking for the net force. And the question that I basically asked was, does the net force point to the left or to the right? Okay, and I proved that the force to the right is bigger than the force to the left, so the net force is to the right. But I was just trying to show that this in general is complicated to do. Okay? Yeah.
If our x component of the force would be less than, let's say, 21, the total work would probably be negative, right?
The total work would have to be negative.
Okay, okay.
Exactly.
Okay, so it's slowing down then.
It would have to be, yep.
And there's an acceleration of that there.
Exactly. Exactly. Okay? What the question was if this was less than 21, okay, would the total work have to be negative?
Yeah.
And the answer is yes. The total work would have to be negative, and the box would have to be slowing down. Okay?
But we can't find the speed, right? We can.
Yeah, part C is if the box is initially moving at 5 meters per second to the right, what's its speed after it displaces 5 meters? Okay, so let's answer that question. And we can answer that question using the work energy theorem. Okay? The work energy theorem just says that the total work, so this is part C, the total work done is the change in the object's kinetic energy. The change is just the final minus the initial. Okay? The initial kinetic energy is 1/2 m times the initial speed squared. 1/2. M is 10 kilograms. What's the initial speed? 5 meters per second. Okay? So that's 25 times 10 is 250 divided by 2. This is 125 joules. Okay? So, the final kinetic energy, all I have to do is add the initial over to the left-hand side. The final kinetic energy is the total work plus the initial kinetic energy, right? I just add this to the left-hand side. The total work we found was positive 155 joules. And the initial kinetic energy was positive 125 joules. So, this is 280. I'm going to add them just to be sure. Yeah. Okay? So the final kinetic energy is 280 joules. Okay? The final kinetic energy, just by this formula, is 1/2 times mass times the final speed squared. Remember, the problem didn't ask for the final kinetic energy. The problem asked for the final speed. Okay? We multiply the 2 up, divide by the m, and take the square root. So the final speed is 2 times the final kinetic energy divided by m, square rooted. Square root of 2 times 280, and m was 10 kilograms. It's 56, square root of 56 is 7.48 meters per second. Okay? Any questions? Last thing really quickly, because we're out of time. This problem can still be solved using kinematics, okay, because all of the forces are constant, so the acceleration is going to be constant. The net force is going to be 52 minus 21, which is 31 newtons. So the acceleration is going to be the net force divided by m, which is 31 newtons divided by 10, which is 3.1 meters per second squared. Okay? We can use the kinematics formula that we're familiar with. Squared equals v naught squared plus 2a delta x. V is going to be the square root of v naught squared plus 2a delta x. V naught, the initial speed is 5. 2 times a is 3.1, and delta x is 5. This is the square root of 25 plus 3.1 times 10, that's 31. This is the square root of 56, and the square root of 56 was exactly what I got here. So we get exactly the same answer. We get 7.48 meters per second. So you see, kinematics and energy are compatible because physics is physics. It doesn't matter which theory or which approach we use. The final speed of this box should just be one number. It should be 7.5 meters per second roughly. Okay? What that final answer is does not depend on what theory you use to calculate it. Okay? It is physically determined by reality. All right, I saw a hand.
Yeah.
Is there a question?
Is it just so basically personal preference what formula you want to use, or?
No, so the thing is that this question clearly sets up a work energy problem. Okay, to answer this question using kinematics, you would have to do a bunch of extra work that you didn't necessarily need to do.
Okay.
Okay? And then we're going to approach problems that we can't solve using kinematics. That we're going to do on Wednesday. So far, every problem that we've solved using the work energy theorem, we've also been able to solve using kinematics. What if we have a problem where the acceleration is not constant? We'll see how to use the work energy theorem on problems that you can't solve with kinematics. Yeah. The 3.1 was A. If you have the pulling force in the x direction, which is 52, and the friction in the x direction, which is negative 21, 52 minus 21 is 31. That's the net force. Newton's second law says the net force divided by the mass is the acceleration. The mass is in kilograms. 1 divided by 10 is 3.1.